Let's talk about missing data. When you're missing data, it reduces the effective sample size for any analysis because you don't have data for that estimation. This becomes a problem when you're missing too much data because it will bias the estimates towards those who did respond. Now in SmartPLS, we can see the missing right here, and if I click on that heading and sort descending, I can see which variables I have the most missing data for. In this data set, you can see there is quite a bit of missing data, but just one or two here and there for these variables. Until you get to the top here, Social Desirability 7 has a lot of missing data. Now the first thing I'd want to do is try to understand why. So I might go look at the wording of that question. Here's my data set. If I go look at Social Desirability 7, here it is right here. Here's the question. It says, there have been occasions when I took advantage of someone else. Well, okay. It makes sense why we might have a lot of missing data on this variable. People just don't want to answer that question. But what can we do about it? Well, one thing we can do is in SmartPLS, we can leave it blank in our data set, and it will just account for it however we specify, listwise, pairwise, or mean replacement. I'll show you that in a minute. But also, when you import the data, this little setup screen will show up, and if you have a missing value marker, like -999, you can enter that here, and SmartPLS will know not to treat that marker as an actual number. It will treat it as missing. That way, you don't have this wildly out of scale value entering into your estimations. Now, SmartPLS knows it is just indicating that that value is missing, not that it's actually -999. Again, this is just if you have placed a marker in your data set. So we can go see in my data set here, if I double click on Social Desirability, you can see it is just blank, blank, blank. So instead of a missing marker, I will leave this blank. Hit OK. Hit Update if you changed anything. I did not actually change anything, so I'll hit Cancel. And when you run covariance-based SEM using the maximum likelihood method with full information, FIML, full information maximum likelihood, the method itself can account for those missing values by bringing in that full information. And so that's what it does by default if there are missing values. Now you can also get specific and tell it how to handle it. I'll just go into this basic model here. And when I go to Calculate and set up the algorithm, over in Data, I can choose whether to use no replacement, meaning omit those rows if there's missing value, mean replacement, case-wise replacement, or pairwise. In most cases where there is not a ton of missing data, and when you have an ample sample size, using mean replacement is sufficient. Now, this all assumes, again, that this is missing completely at random or missing at random. But we don't know that for sure. So, how do we determine that? What we do is a Little's MCAR test. So, over in SPSS, go to Analyze, Missing Value Analysis, and then for the quantitative variables, we would enter every variable that is in our model. Well, we can see the model over here that we might end up using. Just going to move this over here. There we go. And display all the variables. Looks like we're using efficacy 1 through 4, playfulness 1 through 4, ease of use 1 through 4, enjoyment 1 through 4, and skill acquisition probably 1 through 4. Yep. So let me hide all that again and go test this in a Little's MCAR test. Scroll down, grab those variables. There we go. All the variables are now in there. And we're going to click on EM and hit OK. And it produces a bunch of stuff, including a report of what is missing. And it looks like we don't have a large percent of anything missing. The largest percent is 1%, with Playful 4 has 4 missing. But we can scroll down and look at the Little's MCAR test. Now you'll notice they are identical whether you're looking at the covariances or the correlations. Don't know if you can see that. Let me zoom in. It shows the test has a chi-square of 18.4 and degrees of freedom 31 with a sig value, a p-value of 0.963. Is that good? Is that bad? What you want in a Little's MCAR test is a non-significant p-value. So something above 0.05. In this case, we are well above 0.05, meaning our data is truly missing completely at random. It is MCAR. There's not a chance it is missing not at random. Now, if the p-value was less than 0.05, then there's a chance it was missing not at random. But it is really hard to determine that statistically because missing not at random means the missingness is related to variables you did not collect. For example, if you collected data on income but not on age, and you're missing data in the income column, maybe we suspect that younger people tend not to report their income, but older people do. But we didn't collect data on age, and so we can't determine that for sure. So if you end up with a sig value less than 0.05, the best thing you can do is list that as a limitation and use bootstrapping and robust methods for your analyses to help compensate for that. If you have a sig value above 0.05, then you're good to go. If you want to pursue the missing not at random even further, one thing you could do is go to your data set, find the variable that has data missing. Remember we had social desirability 7, which had a lot missing? What you could do is recode this into a new variable that represented its missingness, or whether it was reported or not reported. So every cell that has a value would get a 1 in this new variable, and every cell that doesn't have a value would get a 0. And then you could use that as a grouping variable in a t-test against all of the other variables in your model. If you find any significant differences between those who reported and those who didn't report, then you'll have some indication that the missingness is possibly not at random. But you don't know what variable that you didn't collect is possibly causing that. Well, I hope that helps. In the next video, we will cover univariate influential outliers.